In manufacturing and production, analysts use mathematical concept of finding the optimum value of a function to determine the ideal production rate. Hi, my name is Tom Atwater, and in today's lesson we are going to investigate maximum and minimum values of functions. Let's start with a definition. The definition of absolute extreme values. Let f be a function with the domain D. Then f of c is the A, absolute maximum value on D if and only if f of x is less than f of c for all x in the domain. And B, it's an absolute minimum value on D if and only if f of x is greater than f of c for all x in the domain. Absolute maximum and minimum values are also called absolute extrema. They are also extreme values we call local or relative extrema. Let's take a look at their definition. Local extreme values. Let C be an interior point of the domain of the function f. Then f of c is a local maximum value at c if and only if f of x is less than f of c for all x in some interval containing c. Let's look at what it is for local minimum. The local minimum value at c, if and only if f of x is greater than f of c for all the x in some interval containing c. And a function f has a local maximum or local minimum point at an endpoint c if the appropriate inequality holds for x in some half-open domain interval that contains c. Local maximum and minimum occur on some small interval containing c, and an absolute maximum or minimum is determined by looking at the entire domain. In order to use these ideas, we need a way to determine what values might be maximums or minimums. So we're going to take a look at a theorem called the local extreme value. If a function f has a local maximum value or a local minimum value at an interior point c of its domain, and if f prime exists at c, then f prime of c is equal to 0. We call these numbers critical points. And let's define that very clearly. Definition of a critical point. A point in the interior of the domain of a function f at which the first derivative is equal to 0 or the first derivative does not exist is called a critical point of f. So, in summary, extreme values occur only at critical points or endpoints. Let's look at an example to help us see this. Use analytic methods to find the extreme values of the function on the interval and where they occur. And we have f of x is equal to 1 over x plus the log of x, and the interval we're dealing with is from 1/2 inclusive up to 4 inclusive. So let's find the first derivative of this function y equals 1 over x plus log x. So f prime of x is equal to, well, the derivative of 1 over x we've seen a number of times. That's equal to -1 over x squared. And then the derivative of log x is 1 over x. If I simplify that a little bit, that would be equal to x minus 1 over x squared. And what we remember is that to find a critical point, we look for where the first derivative will equal 0 or where the first derivative does not exist. So we set this equal to 0, and we'll see that when x equals 1, we have that the first derivative is 0. So that is a critical point. So x equals 1. Now what we'll do is we'll find f of 1, which we substitute back in here, and we get 1 over 1 plus the log of 1. Now the log of 1 is 0, and so this is equal to 1, and this will turn out to be a minimum point. Now we have to check the two endpoints, because remember, they could also be either a local max or a local min. So let's start with x equaling 1/2. And we're going to find f of 0.5. And f of 0.5 is going to be equal to 2 minus log of 2 once you simplify it. And that is going to be a local maximum point. And the last thing we have to do is check the other endpoint, which is x equals 4. So we say x equals 4, and we find f of 4. And f of 4 will equal 1/4 plus the natural log of 4. And that's going to be another local maximum point. All right, let's try another example where we use this idea of critical points. Let's take the example, use analytic methods to find the extreme values of the function on the interval where they occur, and what we have is f of x is equal to x raised to the 2/5 power, and the interval that we're going to be working with is from -3 to +1, inclusive of those two endpoints. So I think the first thing to do is to find that first derivative. So we take and we want f prime of x. And that's going to be equal to 2/5 times x raised to the -3/5. Now, we want to know, is it possible for this to be equal to 0? Or is it possible that it's undefined at 0? As it turns out, if you were to graph this function, f of x equals x to the 2/5, it looks like this. Which that is a cusp right here at x equals 0. So we don't have that the first derivative equals 0, but what we do have is that it fails to exist. It's undefined. So we still have to consider x equaling 0 to be a critical point. So we'll work with x equals 0 and the two endpoints, which are -3 and +1. Let's start with x equals 0. For x equals 0, f of x, of course, is going to be 0. And that's going to be a minimum point. And you can also see that from the graph that I drew. Now let's check out the endpoints. What's going to happen is one of them is going to be a maximum, either the endpoint over here for 1 or the one for -3. And again, if I had drawn the graph accurately, we could tell, but let's just plug these in and see what happens. If we have x equals -3, then we want to find f of -3. And that's going to be equal to -3 raised to the 2/5 power, which works out to be the same as 3 raised to the 2/5 power. So of course, if we compare that to the 1 without actually even putting the 1 into the function, we'll see that this 3 raised to the 2/5 power is going to be our maximum point. Okay, identify the critical points and determine the local extreme values for the function y equals x times the square root of 4 minus x squared. Okay, so here's the graph of that function. However, remember sometimes with the graphing calculator, it doesn't give you accurate with respect to the axes. So actually what I'm going to do is fill this in because this graph actually does go exactly to 2 and -2. Okay, so we have our endpoints of -2 and 2, but we can talk about those by saying they are a local max and a local minimum point. If we look at x equals -2, then we would have that f of x is equal to 0. And if we then look at f of +2, that's equal to 0. All right, we still notice that someplace here we're going to have a local maximum, or we'll have a maximum point actually. And down here we're going to have a minimum point. So let's see if we can identify those. In order to do that, we should look and find the first derivative. So let me get to a blank screen, and let's work out the first derivative for this particular function. We have f of x was equal to x times the square root of 4 minus x squared. And f prime will be equal to, we have to apply the product rule, so this would be x times the derivative of the second function, so we would have times 1/2 4 minus x squared raised to the -1/2 times the derivative of the inside, which is minus 2x. And that's just the first half of this. Then what we need to do is add, taking the second function, which is square root of 4 minus x squared, times the derivative of the first function, which is just 1. Let's simplify this a little bit. And actually, when we simplify it as far as possible, it's going to be equal to 4 minus 2x squared all over the square root of 4 minus x squared. We are interested in when does that equal 0, if it does at all. And in order for this to equal 0, that means that the top would have to equal 0. In other words, 4 minus 2x squared is 0. That means 2x squared is 4, so x squared is 2. And that gives us x equals plus or minus the square root of 2. So there are 2 points that we're going to have to check. X equals the positive root 2 and x equals negative root 2. So for x equals the square root of 2, we will plug that in, and well, actually, we don't even need to plug that in, because remember, we looked at the graph. And when we looked at the graph, this is going to be the maximum. And the x equaling -2, negative radical 2, is going to be where the minimum occurred. And that's why looking at the graph turned out to be helpful, because we could tell from the graph that we were going to get some maximum value within this range, and when we calculated it, we get the square root of 2. Well, now it's time for you to try a problem. So let's take a look at the problem that I'd like you to work on. Identify the critical points and determine the local extreme values of the function y equals negative x squared minus 2x plus 4 for x being less than or equal to 1, and it's equal to negative x squared plus 6x minus 4 when x is greater than 1. Pause the video while you work on this problem, and when you're finished, restart the video to check your solution. Let's find out how you did on this problem. The first thing you should have done would be to find the first derivative. So let's take the top function first. So y prime would be equal to negative 2x minus 2. Now, we set that equal to 0 to find the critical points. And when we do that, we come up with x equaling negative 1. So we plug that back into this original function up here, negative 1 squared minus 2 times negative 1 plus 4. So negative 1 squared is positive 1, but then there's a negative in front of it. So that's negative 1. Here we have positive 2, and then plus 4. So that's equal to 5, and that's going to give us a maximum value. Okay. Now, let's do the same thing for the second, or the bottom function, which is let's find the first derivative and set it equal to 0. So y prime here would be equal to negative 2x, and then plus 6. Set it equal to 0 and solve for x, and we'll end up getting that x is equal to 3. And when we plug 3 back into this equation, we get negative 3 squared plus 6 times 3 minus 4. So negative 3 squared is only the 3 is squared, so that's 9, and it's negative 9 plus 6 times 3 is 18. So negative 9 plus 18 for 9, and then subtract 4 from 9, and we get 5. Which of course means that that also is a max. The only other thing we need to do is look at the fact that something is happening at 1. And what's happening at 1 is that the derivative does not exist. So it is a critical point. When we plug 1 into each of these, we will get that it's the same value. So negative 1 minus 2 plus 4. So negative 1 minus 2 is negative 3, plus 4 is positive 1. And that's going to be a minimum value. So those are the answers that you should have gotten on that pause video problem. We have 2 maximum values of 5 and the minimum value of 1. Great. So in this lesson, we explored critical points and used the first derivative to help us determine maximum and minimum, as well as local maximum and minimum values. Be sure to work the exercises that your teacher assigns, and we'll see you next time.